You may have seen the Nernst equation from previous chemistry courses. Here, we're using it to describe the potential across a membrane due to the presence of ions. For instance, if we have potassium ions with a different concentration across the membrane, we can figure out exactly what the potential would be. In a case of a different ion, we just need to keep track of what its charge is, Z, as a function of elementary charge, E. So sodium has a +1 value for charge, so that's a +1 there. Chlorine has a -1 value, so that's a -1 there. Notice that it's the outside over the inside in this case. Okay, now what about if we don't have passive just sitting there from one ion? In fact, in a cell, it's a lot more complicated. We have a lot of ions to keep track of. In this case, we found that the biggest predictor comes down to these 3 ions, and no other ions actually make a huge difference. So, some smart person figured out the GHK equation, which you've actually derived in class. This equation takes into account the concentrations of potassium, sodium, and chlorine throughout the entire cell membrane difference, and takes also into account the permeability of each one. The permeability represents how easily these ions can get across the membrane. If there are channels that are open for potassium, pK will go up hugely and outpower all of these values. So if you know the concentrations of all of these, you can figure out what the membrane potential is. Now remember, all of this applies to just passive membrane potentials. It doesn't take into account what an active sodium-potassium pump would do, which you probably have heard about in previous classes. Passive electrical propagation in neurons is actually a lot faster than active propagation because we don't have to wait for the energy transfer from ATP.